All right, I am ready to begin. I will briefly introduce myself and the workshop. If at any time you're having any difficulties or you cannot see the screen, please ping me on Discord or ask Sean or one of the crew members at, at HitCon, and they will make sure they get the messages to me. Okay, very warm welcome to all of you. Greetings from India. A special note, I wish I could be here with you in person. Sadly, I'm not able to make it, but thanks to all the great efforts by the amazing HitCon crew, and thanks for the warm support and cooperation, we are going to be able to have a very successful workshop today. A number of things that the pandemic taught us. One of the best things that happened is the world eventually came a little closer, and we have learned to work with each other despite any geographical boundaries. And it took us, in a way, it took us a step into the future. Like 10 years ago, I cannot imagine doing this workshop with you, sitting in India and you folks sitting in Taiwan. But here we are once again, and I feel very welcomed and I feel like I'm almost there. My name is Saumil Shah. I have been working in exploit research and many other cybersecurity topics since 1999. I've been teaching, I've been speaking, I've been presenting, I've been publishing papers, and I've just enjoyed being a part of the global cybersecurity community. Today is also very special for me because it marks Indian Independence Day, and we here are celebrating all over the country. So with me, please you know um, join me in wishing all of you a very happy Independence Day. All right, let's get to the setup and the agenda of the workshop. We're going to have about 40-45 minutes discussing about various concepts of ARM64. Ideally, this workshop or the topics that we're going to present will take about one whole day or 1.5 days of active teaching. What I'm giving you is a very curated, quick start into ARM64, ARM64 debugging, simple exploit writing on ARM64. We're going to do some crash dump analysis and work with registers and the memory layouts. And we're going to write a very simple yet a very practical and a very powerful ROP chains and defeat data execution prevention on ARM64 Linux. So we're going to have some theory part which I'm going to work with you through, and then we're going to do some hands-on. I'm going to post some documents on the Discord server in just a moment, and you'll be able to access these documents. One of them is the setup document, which I'm sharing right now. The setup document is basically giving you an idea of how to get your hands-on lab environment going. We're going to use Docker for this workshop. If you have a Mac OS or a Linux host, then you can use Docker natively on Mac OS or Linux. If you have a Windows host, unfortunately, Docker does not work very well on WSL2. We've tried and tested, and then we've given up trying. So if you're using Windows, I recommend you download a Linux virtual machine. There is a download link for the Linux VM in the setup document that I've posted on Discord. Feel free to use it and feel free to refer to it. While I'm giving you a theory overview of the ARM64 environment, you may parallelly start downloading and building the ARM64 Docker volume and the ARM64 Docker container, so that by the time the theory part is done, we can play around with some hands-on stuff. What you're seeing on the slide is already a part of the document. So now I'm going to go ahead and give you an introduction to I'm going to give an introduction to what lies ahead in the workshop. If any time you feel that I'm going too fast, please feel free to message me on Discord and say, hey, Saumil, go slow. We're not able to keep up. If you think you're being very bored, tell me that as well, and I'll try and make things more exciting for you. Okay, so with this, let me just do a quick screen share to make sure you're able to view the screen again. So on the screen, you can see the setup document that I have. Um, Feel free to browse through the setup document and go through it. Basically, what you need to do is you need to clone the Docker containers Git repo. You need to then build the volume, build the ARM64 Docker container. And once everything is built, you simply run the ARM64 Docker container, and you should be dropped into an emulated ARM64 environment. Now, the good news here is once this workshop is done, take this Docker container home with you, use it as a lab, and it's a very quick starting point for you to play around with exploits and play around with ARM64 reverse engineering. Use it as you like. My only access is this is not a free open source container. I would be very grateful if you just keep this within yourselves. This is meant only for the workshop participants. So it's my gift to you, but please do not share it outside yourselves. That's my only humble request to all of you. Okay. While you're building the Docker container, I'm going to give you an overview of the environment, and then we're going to jump in right into the topic. So lab environment is going to be running in a Docker container. There are two main areas of the Docker container. When you run the ARM64 Docker, it's going to start a Docker environment and automatically launch an emulated Debian image running ARM64 Linux. This is going to run in under QEMU, and you have once the environment starts up, you will get to see the prompt. This is what I call as the main console. Once the main console is running, you minimize it. And then every time you want to access the Docker container, there is a command script called ARM64 Docker shell. Every time you launch ARM64 Docker shell, you will get a shell into the environment. It will also give you a menu whether you want to stay in the Docker environment or you want to dive into the Debian environment. We'll cross that bridge when it comes. The other thing you will notice is that there is a shared folder created on your systems. The shared folder is basically a mapped directory which is shared across your host. It is shared across the Docker environment, and it is shared across the emulated environment as well. So anything you edit in the shared environment, you'll be able to use in the Docker environment or the emulated environment. So you don't have to do back and forth copying. It makes the workflow very easy. While you're building and downloading the Docker environment, I'm going to give you an overview of the very quick introduction to ARM64. Now, ARM64 CPUs have been around for a while now. They were first introduced like in 2017-18, and they started becoming mainstream in mobile phones around the same year. And then in 2020, they came to the MacBooks under the name of Apple Silicon. And now ARM64 CPUs are pretty much everywhere. Every mobile phone uses an ARM64 core. iPads, tablets, and now even laptops are starting to move towards ARM64. So it's an architecture which is getting very, very popular, and it's getting quite powerful as well. Now, if you work with the ARM32 CPUs, you will notice that the ARM64 CPU has very little or nothing in common with ARM32. One would think it's just a next step up, but no, in fact, it's almost a very different design in terms of philosophy and in terms of the internal ISA and the internal architecture. ARM32 was largely a RISC CPU, which had very few instructions and very many permutations and combinations of the instructions. If you look at the ARM64 CPU, it is moving more towards a hybrid between CISC and RISC. It has a lot many instructions, and the instructions themselves are also a little restrictive on the ways that they can be used. Now, some of the old concepts of RISC have been let go, and more CISC-like features are being implemented in ARM64. But anyway, for us as exploit developers and reverse engineers, we are mainly concerned with what we see from the software side. The ARM64 CPU is primarily a 64-bit CPU. What this means is that the width of all the registers is 64 bits or 8 bytes. Every memory address is an 64-bit address. All pointers are 64-bit pointers. The contents of any memory operation, when you move data into a register or out of a register, it will be 8 bytes at a time or 64 bits at a time. Now, if we look at the CPU registers, the ARM64 CPU has 31 general purpose registers and 2 special registers. The general purpose registers go from X0 to X30. These are all numbered. While these are all general purpose registers, there are some functional guidelines that are applied to these registers. By functional guidelines, I mean what can these registers be used for, and also what they cannot be used for. So if you look at these registers colored in green, X0 through X7, these registers are largely used for passing parameters to functions. Registers X9 through X15, these are called scratch registers, which are used for all temporary calculations. If you look at X16 to X30, these are also scratch registers, but they are designated as registers that need to be preserved. By preserved, we mean these need to be preserved across function calls. Now let me zoom out a little bit. Whenever we call a function, whenever we're passing parameters to a function, the function does a lot of calculations and computations. So whenever the function works on the data that it's supplied to, it will use registers for all its temporary calculations. Now, the function can use any registers it likes, but if the function uses registers X16 through X30, then the guidelines say that the function must preserve the contents of these registers before changing them. And once the function is complete, it should restore these registers as they were before exiting. So it's like you go to a guest room, you can do whatever you want. But then when you leave the guest room, you put everything back exactly as it was. So these registers will end up being preserved. Now there are 2 other registers which are not numbered. They are the stack pointer SP and the program counter PC. The program counter is a very important register. It points to the next address in the memory from where the instruction is going to be fetched and executed. And the program counter keeps getting incremented to go to the next instruction as well. The stack pointer, as we know, always points to the top of the stack. These are both 64-bit registers and they contain memory addresses. Now, there are two other important registers which I want to point out too, and one of them is going to be extremely important for us in terms of functions, handling functions, and branching. So the two important registers are X29 and X30. X29 is the frame pointer, which points to the top of the stack frame, and X30 is the link register. The link register also existed in ARM32. It was called LR. But here in ARM64, the link register is called X30. You can call it LR, but all other disassemblers, debuggers, everything simply calls it X30. So we'll also call it X30. What these frame pointers and link registers do, we'll cross this bridge a little later when we explore functions on ARM64. Right. So with this, let me go over to the next slide. I want to talk a little bit about the program counter, a little bit about the stack pointer. Then I want to give you a quick overview of 64-bit memory addresses and how process memory layout looks like in 64-bit mode. Then we will get to working with simple examples. Okay. So here's the program counter. Basically, the program counter is an 8-byte wide register, which means the program counter points to an address in the memory. Each instruction in ARM64 is only 4 bytes long, not 8 bytes long. The program counter increments by 4 bytes, and the program counter has to be 4-byte aligned very, very strictly. The stack pointer is also an 8-byte or 64-bit pointer. The alignment of the stack pointer has to be strictly to 16-byte boundaries. These are the guidelines laid very specifically by the ARM64 procedural call standard, AAPCS64. Now, we said that the program counter and stack pointer are both 64-bit pointers. Let's talk a little bit about the 64-bit virtual memory space. Now, whether it is Linux or whether it is Windows or any other 64-bit operating system, the full 64-bit space is never used. So out of these 64 bits, few bits are left reserved, and only the least significant bits are used for the virtual addressing. Now, for most ARM64 Linux kernels, 48-bit virtual memory space is the most preferred memory layout that is used. So once again, in summary, while the registers are 64-bit wide, addresses will only be 48 bits wide. So the way 48-bit addressing works is as follows. Consider like the full 64-bit space broken up in chunks of 256 terabytes. So the first slab of 256 terabytes is used by user space memory. That is, it goes from zeros to FFFFFs, the least 48 bits of it. The last slab of 256 terabytes is for kernel memory space, where the first 16 bits are prefixed with FFFF, and then it goes from 0 through FFFF. All other slabs of 256 terabytes between the first and the last slab are not used, or they're not mapped to any physical memory. So this is how 48-bit memory spaces get mapped in a 64-bit memory land. For us, it really doesn't matter. We're going to be concerned only with the user land in this workshop. 256 terabytes is pretty big for now. I mean, now I say it is 2025. Maybe in 2027, we'll be using up all the 256 terabytes and we'll always want more memory. I don't know. Let me very quickly switch over to discussing how a user land process sees the 256 terabytes of virtual memory. So whenever you launch a process, each process gets 256 terabytes of virtual memory to play with. In this process memory space, you have the binary, you have the shared libraries, you have the heap, and you have the stack, all mapped within virtual memory addresses. So typically in Linux, your binaries are loaded at low memory addresses, which is like hex 400,000. And then you have the heap memory, which grows from the top down. You shared libraries, which are mapped at like FFFFF7. And then you have the stack memory, which is mapped from the bottom FFFFF, and it grows upwards. So this is how typical process memory layouts look like. And if you were to dump the virtual memory layout of a process, you would see something like this on the Linux side. You'd see each binary or library being displayed in a single line. And then you see the memory permissions, whether it's read, write, or execute. You see the start memory addresses, you see the end memory addresses, and you see which path of the binary or the library is being mapped into this memory space. So this is how it all looks like. At this point, I want to just do a quick check around the room and see if we have all the Docker environments running. If everything is go, then we are going to look at I'm going to share another document with you in the Docker channel. This is going to be a walkthrough with all the hands-on and the labs that we are going to use for this workshop. If anybody is facing problems with the Docker environment, please message me in the Discord channel, and I will try my best to help you quickly troubleshoot it. Next, what I'm going to do is I'm going to post a link in the Discord channel. This is an ARM64 walkthrough document. And the walkthrough document describes, basically the walkthrough document is like a full cheat sheet of this whole workshop. Let me show you what the walkthrough document looks like. So we've done step 1, build the Docker container. We've done step 2, that is start the main Docker container. Next, what we're going to do is we're going to download the ROP64 exercises. I recommend you keep this document open on the side and you can work along with this. Then we're going to proceed ahead. So what we want to do now is, if the Docker container is built and the volume is ready, we're going to launch the Docker container. I'm going to follow these steps in section 2, start the main Docker container. We're going to start the Docker container, and then from the second terminal, we're going to launch a shell into the Docker container and see it. Okay, so quick check. I'm going to do a Docker images -a. I have my Docker container ready. Docker volume ls. I have my volume ready. Now I'm going to do a run on 64 Docker. At first, it is going to unpack the file system, and then it is going to start the Docker environment. Now, sometimes for some of you, if you're using a Apple Silicon Mac, the boot up will go pretty fast. If you're using an Intel CPU, it's going to emulate the ARM64 environment. It may not go so fast. The Docker container that I've built is optimized for both the environments. So if you're running on Apple Silicon, it will choose the native QEMU for Apple, and basically it will be just passed through. If you're using Intel, then it's going to be slightly slower. But at one juncture, you're going to come up and see this ARM64 console. I'm also going to put a little poll on the Discord channel, and I'm going to give like 1 minute, 1 or 2 minutes. If you see the poll on Discord, just let me know if you're able to launch the ARM64 console, or if you're getting some errors. I just want to make sure everything's okay. Okay, I think I may have missed some messages. Sean is telling me that my mic volume is not okay. Let me try and see if it's okay or not. So the last sentence I just mentioned is I've just posted a poll on Discord on the HitCon ARM64 HitCon 2025 ARM64 channel. I see a few of you are still working on getting the Docker container going. Not a problem. Once you get the Docker container going, just respond with a success on that poll, and I'll just give a couple of minutes, and then we can go further. All right, so while you're getting that up, for those of you who've got the container working and running, you can launch the ARM64 emulator user shell by doing the following. Just give me a moment. I think I made a slide error in here. So on one terminal, you have the Docker container running. To minimize this terminal, and then you open another terminal and you do a ARM64 Docker shell. So here my terminal is running the Docker environment. I'm going to minimize it. I'm going to launch a new terminal. Change to my ARM64 Docker directory. And then I'm going to launch an ARM64 Docker shell. In the Docker shell, you may go ahead and choose the emulator user shell, option 1. And here we have a shared directory. You go to the shared directory, then what I'd like you to do is clone the clone the ROP64 repository that I have. Once you've launched the emulator user shell, you go to the shared directory, and then you launch the then you clone the Git repo. So this is the git clone ROP64.git. Then you navigate inside the ROP64 directory, and then you can build and run the victim64 elf binary. Okay. So in this ROP64 directory, you will see several files. Our main focus is going to be on this program, victim64.c. Let me show you this code. So here's victim64.c. there is a bug in this code. And if you see the bug, please tell me which line number it is by typing it in the Discord channel where you see the bug. Very good. I got one response. Thank you for that. The name can exceed 80 characters. This is great. Yep. And the problem is with this line, getS. Now, getS does not check how many characters can be inputted. Just waiting for another question to come in. You write SM Apple in enter input more than 80 characters to cause buffer overflow on the stack. That is perfect. So you folks know what you're doing. I'm very happy. That makes my life a little easier. Now what we're going to do is we're going to see this in action. We're going to compile this, we're going to crash this, and then we're going to see how to debug it. And then by the end, we'll have a ROP chain to exploit this. All right. So again, I'll just refer to the document. What we've done is we've gone into the ROP64 directory. We've taken a look at the binary. Now we're going to build the binary and work it. Okay. So to build the binary, make sure you're in the emulator environment with the ARM64 prompt. And then you just do a make. Make will build victim64.elf. Then we're going to run victim64.elf. At first, we're going to simply give it a name without killing it. And then we're going to exploit it properly. Okay, so let me just do a make first. Then I'm going to run victim64.elf. Aha, very good. I get a message on Discord from Janice. We get this error. How do we solve this error? Well, guess what? I'm also getting this error. Now, if you look closely into this error, there's actually a warning. It's not really an error. What do we do with warnings? If the file builds, we ignore the warning. Well, to jokes apart, basically the compiler is telling you there is a declaration error between the official declaration of getS, and it is trying to suggest, like, do you mean this other function? Well, it's just that we've not included the correct header files. Otherwise, so for you it says, I get Janice's error. So Janice's error is it shows an error, no elf file is generated. So Janice, for this, you need to make sure you're in the Docker emulator environment and not the Docker shell. Once again, let me repeat this. When we do a ARM64 Docker shell, do not go into the default part, but choose option 1. And that is the ARM64 emulator user shell. So this is the QEMU emulated environment. You will notice your prompt just says ARM64. And here you go to shared ROP. And here you make it. Then you will see the binary come through. Just sending you this is the screenshot. This is the Docker shell. Okay, let me know if you're still having errors. If you're still getting errors in making victim64.elf, let me know. If not, I will proceed further with the examples. Okay. If you're getting errors, please paste the error message on the Discord channel. I can take a look at it. To do a quick check whether you're in the correct environment or not, do a uname-a. You should be able to see the kernel is an ARM64 kernel and that you're running inside the QEMU emulator. Okay, I'm going to go ahead with the rest of the example. If you still have errors, please message me on Discord. Otherwise, I'm assuming everything is okay and we will proceed with this. So now that we're able to make the victim64 ELF, let me run it. And we will simply give it a name hitcon and test if it is okay. Once it works, we will run it and we will give it a very long list of A's and we are going to crash it and see if we are able to get a core dump. So I ran victim64 and then just gave hitcon 2025. That worked. I'm going to run victim64 and now I'm going to give a very long name. So many A's. If you run this, you get a segmentation fault core dumped and it crashes. What we're going to do now is we're going to recreate this crash in a script. We have a script called exploit1 crash.py. This will generate the input. We will save that input in a file called temp crash. Then we're going to do a GDB on victim64 ELF. And then we're going to run the binary taking the input from temp crash. What we want to see is the effects on the registers. Like once we've overflowed the stack, what kind of registers do we control? And how are we going to then proceed with the exploitation? Okay, I'm getting a couple of questions on Discord. I want to also address these questions for everyone. Here, let me show you my screen if that's working. So one of the questions was someone's facing difficulties doing a Git clone in the emulated environment. I appreciate that. I know sometimes the networking tricks that I'm playing with Docker and Mac and all that can be problematic. If the networking is restarted, it comes back. But if you don't want to do that, there is an easier way. So even on your host, if you go to the shared directory, even on your host, if you go to the shared directory and you do a git clone from the host itself, it should appear within the emulated environment automatically. You don't need to change that. So yeah, I just did the same thing. I cloned from my host, and now if I go to the ARM Docker shell, I go to the emulator user shell, and here I go to cd shared. I will have the ROP64 directory available right here. I can then do a make. And then I do a victim64.elf. And I'm going to crash it again just to make sure the core dump is okay. Great. Well, folks, thank you for your patience for waiting. Sean and crew, thank you again for helping everything out. We will continue. We'll continue going ahead. Okay. Again, folks, if there are any questions, just feel free to message me on Discord. Right. So when we give a very long name, we see that the program has crashed. We're now going to check out a couple of exploit scripts over here. The first exploit script is called exploit1crash.py. And second exploit script is called exploit2pc.py. Let me show you these scripts. So in exploit1 crash, all we are doing is creating 200 A's and then we are outputting it on the screen. We'll save this into a file. In exploit 2, we are very specific. We are doing exactly 88 A's and then we are having 42, 42, 42, 42 and then we are having some dummy shellcode which we will use. So what we're going to do now is we will automate this crashing thing and we will start using GDB. Understand what goes inside the crash dumps and see what we can then do to create our ROP chain. So again, let me tell you where we are in this document. We are now at section 5, debugging and crash dump analysis. We're going to generate the first crash using exploit1 crash.py, create the output into temp crash. Then we're going to GDB victim64.else, and we're going to then do a run less than temp crash. So how to exploit1 crash? It just outputs 200 A's. I'm going to dump it into temp crash. In GDB victim64.else. Sometimes GDB takes time to load. I know it's because it's also loading a lot of extensions. I'm going to do a run less than temp crash. And if everything goes well, you will see like this big crash dump on the screen over here. Just give a couple of minutes to get the crash dump going. So once we have the crash, you notice GDB, I've loaded GDB with GEF extensions. You see all these registers over here, X0 through X30, and you see the program counter and all. So if you notice the program counter, we completely control the program counter. The first 8 bits are reserved for something else, for pointer authentication codes, which is not, we're not going to get into that right now. But if you see, like, program counter is cracked at 41, 41, 41, 41. If you look at the link register or the X30, that's been overwritten with 41, 41, 41, 41. So basically, this is what happens in a stack overflow, right? You overwrite the whole frame, you You control the return address, you control the program counter, and then you crash everything. We have control of the program counter, we have control of the stack memory, we've got basically the building blocks of any exploit. What we're going to do now is figure out how exactly we can control the program counter and how we get all these stack offsets and everything aligned very, very precisely. So if you look at, we're going to do this exploit2 pc.py, and I'm going to dump this into temp pc. Do gdb victim 64.l. I'm going to do a run temp pc. So now if we see with exploit 2, I'm able to do a precise override and get control of the program counter exactly where it is. 42, 42, 42, 42. So now I know I have control of the program counter, I have control of the stack memory over here, and I can actually do very simple exploitation, return to the shellcode and win. Okay, I have a question on the Discord, like someone's new to ARM64. Is the program counter kind of like RIP or EIP register? That's exactly correct. The program counter is a pointer to the next instruction. You're absolutely on target. And since we control the program counter, we can then make the process jump to any address and execute instructions from anywhere that we need. Okay, so we have the crash working. Now what I'm going to do is switch over and explain some crash concepts, and then we're going to see what we can do with this crash. So what happened inside, behind the scenes, is something like this. Let me show you the code. So here in the code, you have main. Main calls function1. Function1 has a local variable called name. You have a buffer overflow into name. Name gets overwritten. The frame for function1 will get corrupted. And then when you return, something goes haywire. With this, let me give you a quick overview of how functions work and how parameters and everything are passed to the function in ARM64. Once we do that, we will work on building the ROP chains. So here's an overview of ARM functions. Whenever you call a function, you're passing parameters to the function. You have a prologue, you have a body, and you have an epilogue. Now in ARM64, Your parameters will be passed using registers x0 to x7. The return address is preserved in x30, that is a link register. When you call a function, the return address is not saved on the stack. It is copied in x30. And to return from the function, you simply branch to x30, and then you have the results back. So in your code, in your function, you'll have the parameters being set in x0 or x1, or in this case, it's w0, w1. You have a branch. BL is a branch instruction, branch with link to the function. The branch instruction will set the program counter to the top of the function, and it will set x30, which is the link register. So this x30 will be essentially the return address, which will be preserved, and the return address will point to the instruction where this function is going to return. Now, when the function returns, there is an instruction in the ARM instruction set called ret, which is very different than the Intel ret. In ARM64, ret is nothing but a branch to x30. So it does not pop or push or pop anything off the stack. It simply branches to where x30 was kept. Now, what happens if x30 gets modified? Like if a function calls another function, then what happens is if x30, if you have a nested function, if that x30 gets modified, then this x30 has to be preserved on the stack itself. So in case of a nested function, if any registers x16 through x30 are changed, then they will be saved on the stack and they will be then restored once the function is cleaned up. So here is an example. If you have a function which makes a call to another function, the link register will be preserved on the stack using this STP instruction. Now, I know we're not going to be able to cover ARM assembly, but I'll tell you what these instructions do. This STP instruction basically stores a pair of registers, x29 and x30, onto the stack at location stack pointer -48. So x29 is stored, followed by x30 is also stored at stack pointer -48. This is what this instruction does. Then, now if you change or you branch to another function, the link register changes. Now, when you return, you will restore these preserved x29 and x30. These are the preserved values on the stack. These will be restored to the actual x29 and x30 by this epilogue. And in this epilogue, you have this instruction called LDP. So this LDP instruction this LDP instruction will load a pair of registers x29 and x30 from the stack pointer and increment it by 48 bytes. So these are the equivalent of ARM64 push and pop instructions. X30 is being preserved on the stack. and then X30 is being restored from the stack. So this is the return address which is preserved and restored. And this is where the magic happens in a stack overflow. So let me show you how the whole thing goes. I'm going to skip this part. And here is how the frame corruption happens. So when you call function 1 will have a local variable called name. This local variable is populated by getS. Before the function goes and sets up the local variable, X30, the return address, is preserved on the stack. Then you have a getS. X30, the return address, is restored from the stack. And then the program counter is branching to X30. This is the whole flow. So let's see what happens when you corrupt the memory. So initially, when your stack begins, before function 1, you have the frame for main. Then the prologue for function 1 will lift the stack pointer up, create the size for the entire frame, and it will preserve X29 and X30 at the top of the stack, not at the bottom. So the return address is preserved on the top. Then you have your local variable name. The getS will overflow the name. Now you will not be able to corrupt the return address of function 1 because that is above the local variable. In ARM64, the frames are upside down. As we know it from Intel and ARM32 or any other processor, the return address is always pushed first. In ARM64, there is no push or pop. You simply lift up the stack pointer and preserve the return address at the top of the frame. So what we will do is we will not corrupt the return address of function 1, but we will corrupt the return address of main. So now your function has to exit cleanly, and when main returns, that is when you will get control of the program counter. So this is how the whole memory corruption is happening. Now to come to the next part, that is data execution prevention. What we're going to see now is, okay, we are able to corrupt the frame, we're able to corrupt the return address of main, we're able to get the control of the program counter. How will we execute our shell code? So one of the theories is like this. Let us say you overrode the string, like here is your buffer, for example. This is the local variable. This is the return address that is saved. Now what you do is, this is the stack memory. You place your shellcode on the stack, you place a whole bunch of mop instructions, and then you take an address on the stack, you simply return to the nops. And then from there, you get to execute your shellcode. This is typically how we have done all the Stack Overflow attacks in the past. But the problem is, you're not going to be able to do this in this case because your stack memory is not executable. You can land in the stack, but you will not be able to execute any code from the stack. And this is because of data execution prevention. So what this means is, we cannot execute arbitrary code by shellcode. We have to choose a different way of executing code. So the idea is, can we still execute a bin shell simply by borrowing assembly instructions that are already present in our program? The whole goal is, we cannot jump to the stack, we cannot jump to the heap. we cannot load our code from there and then execute it because these regions are not non-executable. So instead of executing code that we want to supply, can we not borrow the code that exists in the binary and the libraries directly, and then we get to do code execution? So what I'm going to do from here onwards is I'm going to give you the whole demo of how to build the ROP chains. The document that you have in front of you, the walkthrough document, this document contains all the necessary information you need to find the ROP gadgets, to build the ROP chains, and then the solution is also provided in the Git repo that I shared with you. So I don't want you to feel pressured that, oh, I cannot do everything in this workshop. You can very well take it home and play with it during the rest of VidCon or even after you go home and get a feel for playing with it yourself. Like I said earlier in the workshop today, we are going to compress something that we take one whole day to teach, and I'm going to give you like a nice preview in 80 or 90 minutes. So what I'll do is I'll explain you the core concepts of return-oriented programming. I'm going to show you how the ROP chain is put together, and then we'll do a demo, and then we'll do some questions, and then you can play with this environment and using the walkthrough document, try and make this work on your own. So the idea of return-oriented programming is not new. In fact, it is like, goodness, it is almost 30 years old. This was invented in 1997 and by a very brilliant researcher named Solar Designer. The idea is you don't need to have assembly code to execute Win shell. Why don't we execute a function which we know exists in the library? And this function is called system. Whatever parameters you pass in system will be executed by the shell environment. So what we're going to do is, instead of execute assembly code, why can't we invoke system bin.sh? To do this, we need two things. We need to know the address of system, and we also have to set the parameter to system as a pointer to the string bin.sh. And this becomes an exercise for return-oriented programming. And this is what I'm going to show you now. Getting the address of system is very easy. We can search through libc, and in libc, we know where the library is loaded in the process virtual memory. We know the virtual address of libc, and we know the offset of the function system from the base of libc. Like we have this command in GEF called xinfo. This xinfo command will take a symbol and show you the virtual memory addresses where this function lies or where this symbol lies. So it lies in libc base plus 40890. That's the offset. So if we set our program counter to libc base plus 40890, we'll be able to execute system. But the problem is the parameters. Like how do we pass bin.sh to system? So what we can do is we place the string bin.sh on the stack itself. And then we have to somehow set x0 to point to the stack. If you remember, to pass a parameter to an ARM64 function, we have to do all that through registers. So x0 has to be a pointer to bin.sh. And we need some assembly instruction that will allow us to set x0 to sp. Now, one of these instructions is a move instruction. So somewhere in the library, if we can find an instruction like move x0 sp, we can then control x0, set it to the stack pointer, which points to bin.sh, and then we can invoke system. This is the goal. So with this, let me give you an introduction to return-oriented programming. Most of you who've done binary exploitation might have encountered return-oriented programming. Like, this is not uncommon. In fact, most modern exploits require you to do ROP. So, what return-oriented programming is, we do only one simple operation at a time. We find an instruction in the binary or the library, which does one simple operation. And the next instruction after that is somewhere we can get control of PC again and jump to the next instruction. So typically this is called a gadget. So ROP gadget is basically your ROP gadget is basically an instruction that does what you want to do. That is what we call as a primitive operation, and a branch which allows you to control the program counter and go to the next one. So every gadget has an address. The address is where this instruction lives in the binary or the library. It's going to be like a base address plus the offset to the actual instruction. So what kind of operations can you perform with ROP gadgets? So you can have simple operations like set x0 equal to an arbitrary value. You can have a read memory operation, that is, take an address and read memory from that address into a register. Or you can write memory. You can take an address and copy the contents of a register into that memory. Basically, all you need are these simple operations, that is, set a register to a value, read contents of a memory in the register, or write arbitrary values from a register into memory. If you can do these three things using gadgets, you can pretty much do whatever you want. The second instruction is a jump, which will get you which will basically allow you to jump to the next gadget. So essentially, how a ROP chain is going to look like is something like this. On the left-hand side, you have the stack. So you have a local variable which is overflowed, which is all these AAAs. This pink region is the return address, which will be the preserved X30. Now, when you gain control of the program counter, you make the program counter jump to a part of the binary of the library, which has the address of the first gadget. So this will have the first operation. Once the first operation is done, the program counter will then go pull the address of the next gadget and then jump to the next gadget. Next gadget will pull the address of the third gadget and jump to the next gadget. So this is how the whole thing is going to flow. So to put this whole perspective together, you can do these exercises on your own. I have the examples in the document, but I'm going to show you. We're going to do two things. We're going to prepare a ROP chain as follows. So first thing we're going to do is we're going to have a gadget which will get us the address of system into X1. So on your stack, what you do is you place the address of the gadget. The first time you get control of the program counter, it jumps to this gadget. This instruction over here will load X1 from stack pointer plus 18. The value that is being loaded into X1 is this value, the address of system. This is then set in X0. And then the gadget ends with a load X30 from the stack. So the next gadget is going to be at this location 49, 49, 49, 49. This gadget is replaced with an add gadget, which sets X0 equals stack pointer plus hex 10 bytes. Now what you do is you place the bin sh on the stack. you set X0 that points to bin sh. There's an XOR operation that happens as a part of the gadget, which we cannot avoid. So we will have a pre-XORed value. Instead of the address of system, we'll have a pre-XORed value of system. This will get de-XORed over here. And the last instruction is a branch to X1. At this point, X1 contains the address of system. You branch to system, and then you will get a shell. I'm going to do the final demo of this, but basically what I gave you is a very quick overview of how to put the whole ROP chain together. This yellow part is how to overflow the local variable. Then when you get the return address, you jump to the first gadget. The first gadget sets the address of system in register X1 and goes to the second gadget. The second gadget sets the parameter X0 to stack pointer plus 10, where you have bin sh, and then it branches to X1, which is the address of system. And when you land in system, you get control of the parameter, and it will launch a shell. Let me show you the demo over here. So in your ROP64 directory, you have this script called solution.py. These are the gadgets that you see. I've tried to comment the whole code. So first I found the address of the libc base. Then I found the first gadget to load X1 with the address of system. Then I have that. So I have a variable called gadget1, which is libc base plus the offset of the gadget. Then you have the second gadget to set the parameter X0 to stack pointer plus X10 and branch to X1. So this is the address of the second gadget. This is the address of system. And this is the ROP chain. So you have the 88 A's. Then you have the gadget 1. Then this is just padding. This is gadget 2. This is the address of system with the XOR. And here, instead of bin shell, I am executing three commands: id, uname-a, and ls. You can join any arbitrary commands over here. I can also do like a ps, ax, or however many commands that I like. Then I create the ROP chain, and then it'll be done. Again, what I've showed you is essentially all this. We did the crashes. We did this. Here's a ROP chain template that you can play with. Here are instructions on how to search for the gadgets using ROPer. These are the commands to search for the gadgets. These are the gadgets that you can find. This is how you find the address of system and libc base. Then this table shows you all the gadgets that we need for the ROP chain. And then this is the solution that we have. So even though I had to speed things up, I want to make sure you have all the material that you need to play with this and practice this yourself. If you have any questions, you can ask me on Discord. I'm going to keep this channel open, and I'm going to be able to answer your queries as and when during my day or even tomorrow, not a problem. Let me show you the final demo. So here is the solution script. This is the payload for the solution. Part of the payload overflows the local variable, and all this stuff are the gadgets. And then in the end, you have these 4 commands. If I now run solution.py and pipe it to victim64.elf, here you go. It asks you for your name. The name is this big string that we supplied. And if all the gadgets are correct, you get the commands executed. You have the ID command, you have the uname command, you have the file listing command, and you have the process command. So basically, and then it says stack smashing detected code dump. But you've got all your code execution and everything working really wonderfully. And essentially, this would be a simple but a very powerful exploit which works on ARM64 and bypasses data execution prevention. So I know things got a little fast towards the end, but I hope you had some good learning. I hope you had some good ideas that came from this workshop. My goal was to give you a introduction to all this stuff and get you enough tools in your hands to practice with this and play with this on your own. Again, if you have any questions, please pop them on Discord. I'll be monitoring the channel all day. And although I'm sitting in India, I'm kind of with you already for the next 2 days. So consider me as part of your team. And again, thank you very much, FitCon group, for all your help and all the support you showed me. Thank you, participants, for joining me and being patient with all the exercises. And wish you have a wonderful time in Taiwan. And I'll see you folks sometime soon. So, thank you very much.